We are Team Bread. My name is Roba El Sheikh, the project manager. I'm accompanied with Amati Pute, the design specialist, Andrew Brewer, the financial analyst, and Brandon Drew, the safety officer. And today we're going to present our styrene production. This presentation will cover Bread's proposal for a feasible, profitable, and safe production of manufacturing styrene. Here is an outline of what we will be covering during this presentation. Styrene is commonly known for being used to manufacture latex, synthetic rubber, and polystyrene resins. The global market for styrene has significantly risen due to the growth of packaging and construction industries. The SRK thermodynamic property method was selected to successfully carry out the simulation on aspen. By the dehydrogenation of ethylbenzene using a large quantity of steam at a high temperature and low pressure, we were successfully able to achieve a production rate of 113,000 tons per year and a 98.7% styrene purity. The plant's location is based in Oakville, Washington. The cost of manufacturing is $230 million with an annual production profit of $186.5 million with a 0.6-year plant payback. Shown here is the overall material mass balance. Ethylbenzene, benzene, and water are fed into the products and mixed with superheated steam. The steam to ethylbenzene ratio is 13:1, enough to achieve a heated reaction to produce styrene and its byproducts. The values were obtained from the outlet streams of the three-phase separator, distillation tower 1, and distillation tower 2. And the products that are being produced and sold are styrene, and with further distillation, we can sell hydrogen, ethylene, and benzene. This is the kinetic data used in Aspen to achieve the reaction in the reactor. The two important principles of thermodynamics were considered, which are chemical equilibrium and chemical kinetics. The equilibrium constant determines how far the reaction can possibly proceed given sufficient time for equilibrium to be reached, while the chemical kinetics determine at what rate the reaction will proceed towards the maximum extent. These values were obtained from a styrene research paper and verified on Polymath.
This is our process flow diagram. The reaction of ethylbenzene to styrene is endothermic and reversible, so high temperatures and low pressures are conducive to high conversion in the isothermal vapor phase reactor. Steam is mixed with ethylbenzene and fed to the reactor to lower the partial pressure of ethylbenzene and increase conversion. There are also several other side reactions that produce undesirable byproducts, such as benzene, toluene, ethylene, and carbon dioxide, whose reaction rates increase with temperature and partial pressures. The advantages of using steam are 1, it can provide the heat to maintain the reaction temperature, and 2, it shifts the equilibrium conversion to a higher value by diluting the mixture and decreasing the partial pressures of ethylbenzene and hydrogen. The required energy of reaction is supplied from latent energy of injected superheated steam. Thus, the reaction taking place causes a decrease in the temperature of the bed and, subsequently, the conversion of ethylbenzene is decreased. The exit stream of the reactor is hot and gets cooled through multiple exchangers. By using the temperature interval method for exchangers, we were able to conserve energy by connecting streams 3 and 8 and allowing them to transfer heat. Stream 10 reaches the separator at 75 degrees Celsius and 2.5 bar, enough to obtain the organics and remove the gaseous products and wastewater. These gaseous products could be used to sell, but Austin will touch on that later on during the economic analysis. After exiting the separator, the organic stream goes through the distillation columns to remove each product at a higher temperature and low pressure. Styrene gets removed in T102 at the bottom, and the exit of the top gets recycled back into the stream. Now let's get into our process design specifications. The R-plug reactor used in Aspen is the best choice to simulate plug flow configuration with the composition changing along the reactor length or catalyst mass, since it allows the full definition of kinetics and hence the prediction of reactor output under widely different conditions. The catalyst we used is iron oxide. You'll see that there's a very small amount of toluene and styrene entering the reactor. This is due to trace amounts remaining in the recycle stream. For the distillation columns, the model we used in Aspen was RadFrag. They have a partial vapor condenser and a kettle reboiler. To determine the stages, we had Aspen output a reflux ratio over a range of theoretical stages. We multiplied the theoretical stages by these reflux ratios and graphed them over theoretical stages to find the minimum value, which we then used for the selected stage. For T101, this was 16, and for T102, it was 88. Our feed location should ideally be around half the number of stages. We increased it slightly to ensure a good separation. We used this method to balance economic feasibility and efficiency of the towers. The reflux ratio and distillate to feed ratio were both obtained in Aspen. For the separator, we used the Flash 3 model in Aspen.
For the safety aspect of our plant, we first looked at the materials that we would be working with. It was found that most of our materials were toxic and flammable. This put a large emphasis on the importance of containment for our materials, for a leak could cause environmental harm and/or an explosion. This is the main concern for our plant. We also see, while looking at the reactivity worksheet, that there is a complication of mixing ethylene, hydrogen, and our styrene monomer. It is said that these together will most likely polymerize and cause a rapid gaseous mixture that may lead to overpressurization and a possible pipe or equipment rupture. Since this is in direct correlation to a containment problem, it heavily influenced the valves and controls of our PNID. Moving on to the reactor HAZOP and PNID. The HAZOP was based on a risk ranking scale of 1 to 3 by using a matrix between likelihood and severity ranging from 1 to 5 and were solved. Sums of 1 to 5 were ranked as 1, 6 to 7 were ranked as 2, and 8 to 10 were ranked as 3. Where 1 was represented by green and required no action, 2 was represented by yellow and an action was considered, and 3 was represented by red and an action was required. Some of the required and considered actions consisted of a high flow which could lead to a loss of containment, and this was mitigated by flow sensors. We could also have a high pressure in the reactor which could lead to overpressurization and an explosion, and this was mitigated by a pressure relief valve to a flare. We could also have low pressure in the reactor, possibly causing an implosion, and this was mitigated by a pressure sensor. We could also have a high temp leading to a burning of product and damaging the catalyst, and this was mitigated by an inlet temperature sensor, flow controller, and a high temp alarm. And lastly, corrosion, which could lead to a loss of containment, and it can be mitigated by regular maintenance. Moving on to the separators and towers. The same problem would occur for each of the 3 pieces of equipment, such as high pressure in the gas line, which could cause pipe rupture. This was mitigated by a pressure relief valve. We also have corrosion, which could lead to loss of containment, but would be mitigated by regular maintenance, which would also take care of the possibility of equipment failure. Lastly, we considered the possibility of a lack of flow, or flooding of the separator and towers. This was mitigated by adding a level controller.
Our group chose Oakville, Washington for our location due to its ease of access to the coast. This makes it much easier to bring in our raw product from our Chinese suppliers. Now, for some land specifics, the piece of land we settled for was 6.6 acres and $65,000 with direct river access. This is relatively cheap, especially considering the river access and the conveniences that would bring us for transportation. Not only do we have this convenience though, but in Washington, they utilize a gross receipts tax instead of a typical income tax. The gross receipts tax actually taxes you based on the gross revenue at a smaller percentage opposed to the net income like a normal income tax. This can pose a problem for startup businesses that aren't bringing in a lot of net profits, but is a huge boost for our facility due to our large net profits. Now for that economic analysis of revenue. Shown here are 4 products. However, you can see that I have benzene, hydrogen, and ethylene actually making us $0 at the moment. This is because we do not refine these products down to levels that are reasonable for sale at large profits, and I set a conservative guess for the profit for each of these to be just about equal to the cost of freight to another facility for further refinement. Now that leaves us with just styrene that is driving our annual revenue of $416 million per year. This next slide shows an analysis of our fixed capital investment costs. This is a snippet from our cap cost sheet that was used to estimate our equipment costs. Here you can see we have 4 main contributors, being each over $1 million. They include our 2 process heaters, 1 of our distillation towers, and a reboiler that comes right off our main distillation tower. This all adds up to about $80.8 million per year. Now for our utility costs, you can see we also have three main contributors, being one of our heat exchangers and two of our process heaters, and it all equates to about $4.1 million per year. Now for the total analysis, starting with a fixed capital investment was shown at $80.8 million, and then we have our labor costs, which is just under $1 million, and these are based on the number of units that would require operators to monitor them, and an operator's salary for $62,000 per year. The raw material cost was about $168 million a year, and it makes up our ethyl benzene costs from our Chinese suppliers, along with the city water costs in order to produce steam. And next we have utility costs of about $4.1 million, which was shown in the previous slide as well. And lastly, we have our wastewater costs of about $13,000. This is the cost for purifying the water that comes in direct contact with our process fluids to purify some of the organics. This all equates to about $230 million per year for our cost of manufacturing without depreciation. And if you include an average depreciation of $8.1 million over 10 years and an annual revenue of $416 million, that brings us to a taxable net income of $178 million. This shows why we were glad to see a gross receipts tax instead of a typical income tax. However, our average cash flow is the net income plus the average depreciation, since you're not actually losing the money that's actually being depreciated for the equipment. So keep this in mind. Next, you can see our projected cash flow for the life of the project of 12 years. This includes a net present value of just over $1 billion, a discounted payback period of 0.6 years, and a discounted cash flow rate of return of just shy of 100%, all unheard of numbers for an investment of this magnitude. However, we all know that investments do have some risk involved with them, so to account for some fluctuations, we use a Monte Carlo method for risk analysis. To account for some inaccuracies in the estimation of the capital cost, we used a negative 20 to a 30% fluctuation on fixed capital investment. For the price of the product, we decided that the styrene cost was relatively high at the moment due to certain circumstances, so we decided on a negative 20% to a 5% fluctuation based on some of my other conservative estimates, such as my byproducts making zero money. We decided our working capital was about accurate, but we put a negative 5 to a 5% fluctuation based on some noise in the data. And then the income tax rate was scraping the bottom of where it could be, and the interest rates are also extremely low due to current circumstances, so we put each of them at 0 to 10% fluctuations on both of these rates. Now, the raw material pricing we used was negative 10% to a 10% fluctuation, just to account for the inherent noise in material costs from day to day. And we decided that the salvage value would also be about the same value, or same range as the fixed capital investment. With all that being said, the net present value ended up ranging from about $400 million to about $1.1 billion. Our discounted cash flow rate of return was about 100% to 200%. And our discounted payback period was between 0.25 and 0.6 years. Again, all unheard of numbers. So it ended up being a very high rate of return and a very safe investment.
Through this presentation, Team Bread committed to ensure the best possible methods of operations to produce the most efficient styrene production design. Our team approached each step of the design carefully in preparation of presenting a safe and economical plant. Given the high demand of styrene-based products, an investment for Bread's design will allow for a 90% conversion and a 98.7% styrene purity, and an annual profit of $183.5 million with a 0.6 plant payback. Our design is operated in the safest conditions based off our safety analysis, with a competitive operational pay rate to employees, and still are able to achieve a profitable profit margin at the end of the day. That is why we strongly recommend for you to invest and trust in Bread. Here are references. Thanks for watching our presentation, and we hope to hear from you soon. Thank you.